The contemporary scientific narrative of the universe's origin commences with a colossal explosion that triggered the expansion of space itself. Approximately 15 billion years ago, all the matter and energy constituting the observable universe were confined within a space smaller than the head of a pin. The universe then underwent an incomprehensibly vast explosion known as the Big Bang. Following this event, both the substances that make up the universe and the fabric of space itself initiated an expansion in all directions, a phenomenon that persists to this day. Nonetheless, an intriguing force is at play in the universe, casting a peculiar shadow over this explanation. Instead of expanding uniformly, the expansion is exhibiting unusual behavior, with something anomalous occurring at its peripheries. This results in matter moving away from us at an accelerating rate the farther it is from us. This acceleration is not characteristic of most explosions. Scientists attribute this behavior to dark energy. But what exactly is dark energy, and why do many scientists have confidence in its existence? What implications does this hold for our understanding of the universe? Our universe is considerably more enigmatic than it initially appears. Our systematic exploration of the universe's structure only began in earnest within the past century. While we possessed knowledge of stars prior to that, it was a revelation to determine the actual distances to some of these stars. Prior to the 1920s, scientists largely believed the universe consisted of just one galaxy filled with stars. Although some astronomers had speculated the existence of island universes, actually other galaxies in the sky, it wasn't definitively proven until the 1920s, when American astronomer Edwin Hubble undertook observations. In 1923, while studying what we now identify as the Andromeda Galaxy, Hubble recognized a Cepheid variable star among the stars he was observing. Cepheid variables are stars that exhibit periodic variations in brightness over a span of weeks, and their luminosity is directly linked to their period. By measuring the regularity of the star's brightness fluctuations, Hubble could calculate its expected brightness. By comparing this expected brightness with the observed brightness, he could mathematically calculate the star's distance. This discovery provided astronomers with a means to measure the size of the universe. Hubble's findings were startling. The star he was investigating was so distant that it had to exist outside of our galaxy. This revolutionized our comprehension of the universe. However, another surprise soon followed. Hubble observed another intriguing phenomenon: an expanding universe. This observation was so unsettling that even Albert Einstein, the German theoretical physicist who had previously challenged conventional notions of space and time, struggled to accept it. Einstein had proposed a cosmological constant to stabilize his equations and maintain the static nature of the universe. He couldn't readily embrace the concept of a dynamic and ever-changing universe. But as time progressed, it became evident that Hubble's observations contradicted Einstein's static model, making the cosmological constant unnecessary. Hubble's observations were rooted in the Doppler effect, which dictates that the wavelength of radiation extends when its source is moving away and compresses when it's moving toward the observer. By understanding the expected frequencies of light from galaxies and applying the Doppler effect, Hubble determined that all galaxies were moving away from us. This realization naturally led to the development of the Big Bang theory, but a vexing question remained. Galaxies weren't just receding from us. They were doing so at an accelerating rate. Acceleration necessitates energy, and the source of this energy remained enigmatic. This mystery prompted scientists to propose the concept of dark energy. When scientists applied general relativity to the expanding universe model and compared it to the latest observational data, they deduced that the visible particles, or baryonic matter, accounted for only 5% of the universe's composition. The remaining 95% presented a shortfall, and it appeared that matter was behaving in an unusual manner, as if some invisible, gravitationally influential entity were at work. This invisible substance was termed dark matter and was believed to make up 27% of the 95% shortfall. The remaining 68% was ascribed to the energy responsible for the universe's expansion. This energy was undetectable, invisible, and pervasive, supported by mathematical calculations. Several theories emerged regarding the nature of this energy. Einstein's cosmological constant made a reappearance, postulating that empty space possessed energy that could give rise to more space and energy. This concept, however, lacked a detailed explanation. Another theory suggested that virtual particles, created momentarily due to quantum mechanics, could contribute to this extra energy by briefly exerting force before annihilating. While this theory had some experimental support, the calculated energy produced by virtual particles was exceedingly excessive, leading to skepticism. The third theory proposed a varying cosmological constant, rather than a true constant, acting as a field akin to electrical or gravitational fields. This field, known as quintessence, could be the fifth fundamental force of existence, but it failed to provide a satisfactory explanation for its existence. In summary, the study of dark energy remains a poorly understood field, and further research is needed to draw accurate conclusions. Detecting something invisible is inherently challenging, but efforts to study dark energy through its influence on the universe are already underway, with different observatories employing distinct methodologies. For instance, the Bingo telescope in São Paulo, Brazil, aims to monitor the radiation emitted by hydrogen atoms in dark regions of space to identify unusual matter distributions hinting at dark energy's influence. The universe's peculiar tendency to form matter in waves, with a typical distance of around 500 million light-years between galaxies, suggests that studying the gaps between these waves could provide valuable insights into dark energy's impact. For a more comprehensive investigation of dark energy over time and space, the European Space Agency, ESA, has launched the Euclid Space Telescope. Euclid, equipped with a 600-megapixel camera, is designed to capture visible light and infrared radiation from a significant portion of the sky with unprecedented detail and precision. Its mission is to create a 3D image of dark energy's influence, allowing us to examine how this influence has changed or remained constant over billions of years. Euclid aims to offer valuable insights into the nature of dark energy and the completeness of our understanding of the laws of gravity. While Euclid's mission began in 2023, it remains an ongoing effort to shed light on the mystery of dark energy. This elusive force, which constitutes over 60% of the universe, remains largely undetectable and exerts its influence by driving galaxies apart. As a result, it is possible that, in the future, we may only be able to detect our own galaxy, as all others will have been pushed beyond the limits of observable light. Whether the universe's expansion is eternal or whether dark energy will eventually wane is a subject of ongoing inquiry, with Euclid and time potentially holding the key to further revelations.